Hi, welcome to the next in our series of Practical Electromagnetics for Engineers. Today we're going to talk about another matching technique that doesn't use a stub. It's something called quarter-wavelength matching. This is going to be short, but it's actually very useful because this technique is not only used in transmission lines, it's used on radar domes, other things where you need to get electromagnetic energy through a material with minimal losses. You even use it in optics. For example, if you wear glasses and you have an anti-reflective protective layer on those glasses, this is the techniques that's used to create that. So how does it work? What you do essentially is you put a short section, 1/4 of a wavelength long, right between the load, which we assume to be mismatched. So let's write that on here. We know our load does not match to the line. You put a short section of a different impedance transmission line, and we're going to call that different impedance Z1, between the line and the load that's exactly a quarter wavelength long. So why do we use a quarter of a wavelength? Well, that's actually pretty simple. Let's assume that we've got a wave, and let's basically make our wave look something like this, and we know it's coming in from this direction. A quarter of a wavelength later, when it hits the load, we know we're going to have gone through 1/4 of a cycle of the wave, so the wave is essentially going to be down like that. We know that we've got a mismatch here at this terminal and a mismatch here at this terminal. So we're going to get some reflection from this terminal, and that reflection is essentially going to result in a wave that goes back like that, in that direction. We're also going to get a mismatch here, and this wave essentially is going to come back like that, a quarter of a wavelength in length. Well, what happens is the two waves, the one that bounces back from there and the one that bounces back from there, happen to be 180 degrees out of phase because the total round-trip distance from here to here and back again is half a wavelength, and waves that are half a wavelength apart are 180 degrees out of phase. So let's take a look at that in a slightly better case right here. We can draw this up a little bit better. Let's draw our axis here. And let's assume with a quarter of a wavelength, we'll start high, we'll come down a quarter of a wavelength, it reflects, we come back, and so the reflected wave from the load is going to look something like that. The reflected wave from this point, where the incoming wave reflects, and so there's our incoming wave, is essentially going to be, and let's draw this with long dashes, dash, 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 and you can see that those two reflections are going to cancel each other out everywhere along the line. And this works whether Z load is greater than Z naught or Z load is less than Z naught, because if Z load is less than Z naught, you get the same phase shift. So what's the value of Z1? What's the value of the impedance that has to be on this little section of line midway between the load and the line that's exactly a quarter wavelength long? Well, that's fairly straightforward. We know that beta Z for a quarter wavelength section is lambda over 4. Or, excuse me, that's not lambda over 4. When we plug in lambda over 4 to Z, we know beta Z turns out to be pi over 2. We know E to the imaginary pi over 2 is just the imaginary number I or j. Negative pi over 2 is negative I or negative j. And when we plug this in and we also substitute for our reflection coefficient Z load minus Z naught, actually we've got two of them. We've got Z load minus Z1 and Z load plus Z1, and the same thing for Z naught and Z1 for calculating those two reflection coefficients. But when we calculate that, it turns out that the input impedance at a quarter wavelength is equal to this expression right here at this point in time when we calculate the input impedance right there. And so that's fairly straightforward to calculate. If we say we want Z in to be equal to Z naught, so we can match right there, then we know that Z naught equals Z1, that's our quarter wavelength section squared, over Z load, or in other words, Z1 is equal to the square root of Z naught Z load. And if we choose this impedance for our quarter wavelength section right here, we get a perfect match between a mismatched load and a line. And this doesn't require a stub. It takes up less space on a printed circuit board where you can custom manufacture the impedance by the widths of the line. It's harder to do when you have to go out and buy sections of actual coax cable or transmission line. But you'll see this a lot when you look at things that are driving antennas. For example, here's something called a patch antenna. And so the patch antenna, and this is what's in your cell phone actually, is that section right there, and you'll notice it's got a feed line coming in, but also a section of line that's of a different width right here to drive that patch antenna. And this happens to be a quarter wavelength section to match the impedance of this line to the impedance of the antenna, because there's a built-in mismatch for the type of antenna they wanted on that. And that's all there is to it. Very useful when you're building anti-reflection layers in optical devices, on doing PC boards and things like that.